All right, today we're going to dive into a technology that it's completely changed the game for engineering. We're talking about everything from the car you drive to the medical implants that literally save lives. It's called finite element analysis, or FEA for short. And it all really kicks off with one simple question, right? How do you crash test a brand new jet design without actually building a $1 billion prototype? Or how do you see how a new bridge is going to hold up in a hurricane that hasn't even happened yet? How do you model the stress inside a human heart? Well, you do it with FEA. It's the ultimate virtual proving ground. So what is this incredibly powerful tool, really? At its core, FEA is, well, it's a brilliantly simple solution to some of the most complex physical problems you can possibly imagine. Okay, so the big idea here is it's actually simple, but it's also kind of profound. See, instead of trying to solve one single, gigantic, impossible equation for a whole object, FEA just breaks it down. It chops the object up into thousands or even millions of these tiny, manageable little pieces, and we call those finite elements. Think about it like this. You take a real-world object, something with all these beautiful, complex curves and holes and little details, something that a computer would have a really hard time understanding all at once. And then you basically throw a grid over it. We call that a mesh. And just like that super complex shape is now just a collection of simple shapes, like little tiny triangles or cubes. And now the computer can go to work. It can run the math on each simple piece, one by one, and then it puts all the results back together to predict how the entire thing is going to behave. So how does an engineer actually do one of these virtual tests? Well, the process is really logical. It breaks down into three main stages. So first up, you have the pre-process. This is where the engineer lays out the whole problem, right? They define everything. What's this thing made of? What kind of forces are we talking about? Is there heat involved, pressure, all that stuff? Then the computer takes over. That's the process stage. It builds that mesh we were just looking at, and then it just crunches the numbers. It solves all those complicated equations for every single element. And finally, you get to the post-processing. This is the payoff. The engineer gets all the results back, usually as this awesome color-coded map that shows you exactly where the stress is, or the hotspots, or the vibrations are on the whole object. And this three-step process, it's the engine that powers some of the most advanced engineering on the entire planet. You probably don't even see it, but FEA is working all around us every single day. Just think about the transportation and aerospace industries. The stakes there are unbelievably high. FEA is absolutely essential for things like simulating the integrity of aircraft landing gear, analyzing the aerodynamics of a new plane, or, and this is a big one, running thousands of virtual crash tests to make our cars safer, long before any real metal gets bent. And it's just as vital for the infrastructure we all depend on. Engineers use FEA to make sure our bridges and dams are safe, to optimize the shape of wind turbine blades so they get the most energy, and to analyze the incredible stresses happening inside power plant boilers and oil pipelines. But maybe the most amazing, the most breathtaking application of FEA is when we turn this incredible tool inward to model the most complex machine of all, us, the human body. This is really where FEA goes from just engineering to saving lives. Biomedical engineers are using these exact same principles to simulate how our bodies work and, more importantly, how we can heal them. It's applying this analysis on a deeply personal, biological level. Just let these sink in for a second. Simulating head impacts to design better helmets. Analyzing the exact contact pressure inside a knee joint to create longer-lasting replacements. And designing cardiovascular stents, those tiny little mesh tubes that save so many lives, by modeling exactly how they'll interact with our blood vessels. It's just incredible. Now, as you can probably guess, running these kinds of life-or-death simulations isn't just a matter of clicking a button. For the experts who do this work, a huge part of the process is choosing the exact right tool for the job. So for the pros, the question isn't, should we use FEA? It's a given. The real question is, which FEA software are we going to use? And in the world of structural simulation, two big names always come up, ANSYS and Abacus. Picking between them is a major engineering decision. And they both have their own strengths, ANSYS is often the go-to for its speed and its amazing ability to combine different kinds of physics in one simulation, like how structural stress and fluid flow interact. Abacus, on the other hand, is really the king when it comes to super complex stuff, like fractures and extreme deformations. It gives specialists this really deep level of control. So, with all this sophisticated technology, these specialized tools, and life-saving applications, you might think this is a pretty recent invention. But the truth is, the core idea behind it has been changing the world of science and engineering for a very, very long time. Yeah, this revolution, it did not happen overnight. It's been building for decades. For 80 years now, the finite element method, that's the mathematical foundation that all of this is built on, has been growing and evolving. What began as this kind of niche technique for analyzing structures has blossomed into one of the most important tools in modern history. And this quote right here, it just says it all. The finite element method has become the computational workhorse for pretty much any problem you can describe with something called partial differential equations. Now, that's just a fancy term for those impossible equations we mentioned at the very beginning. The fundamental physics that govern everything from how heat flows, to how fluids move, to how electromagnetism works. So, after all that, after seeing how FEA works, where we use it, how long it's been around, what's the one big thing you should really take away from all this? I think it really comes down to this. In engineering, there's almost never one single best tool. It's always about finding the right tool for that specific job. But honestly, it's bigger than that. Finite element analysis, it represents a huge shift in how we even think about solving problems. We've moved away from just building something and then breaking it to see if it works. Now we can predict and perfect it, all in a virtual world. It's this whole philosophy of taking something that seems impossible and breaking it down into something possible. And really, what is that if not the very heart of modern engineering?